Connecting the X0 terminal to the transformer frame is essential. The X0 terminal represents the neutral point of the transformer's secondary winding. Connecting it to the transformer frame creates a necessary path for fault currents, ensuring the secondary system is properly grounded. Refer to National Electrical Code Section 250.28 A2 for more information. Next, bonding the panel board neutral to the panel board frame is also essential. The neutral conductor and the frame of the panel board must be securely bonded together. This bonding step ensures the proper grounding of the secondary distribution system. See National Electrical Code Section 250.24. C5 for details. Mounting the insulated ground bar on the bottom of the panel board is acceptable. The insulated ground bar can be positioned either on the bottom or on the back panel of the panel board. The primary requirements are easy accessibility and the provision of a separate, isolated pathway for insulated equipment grounding conductors. Consult National Electrical Code Section 250.138 for additional requirements. When it comes to the bonding wire size for X0, it must be at least 2 AWG or larger. The National Electrical Code mandates a minimum conductor size of 2 AWG or larger for bonding the X0 terminal of a transformer to the transformer frame. This requirement helps ensure a low impedance path for fault currents. See National Electrical Code Section 250.66 for additional requirements. Overall, connecting the X0 to the transformer frame is essential for safety. Bonding the panel board neutral to the frame is also essential for safety. The location of the insulated ground bar is important for accessibility. The bonding wire for X0 must be the proper size. Now let's delve deeper into each of these aspects, providing a more comprehensive understanding of the requirements and best practices. Grounding the X0 terminal to the transformer frame is not just a matter of code compliance, it's a fundamental safety measure. When a fault occurs in the secondary system, such as a short circuit from a phase conductor to ground, the fault current needs a low impedance path back to the source to quickly trip the overcurrent protective device. This path is provided by the connection between the X0 terminal and the transformer frame, and then through the grounding electrode conductor to the grounding electrode system. Without this connection, the fault current may find other, less desirable paths, such as through equipment grounding conductors or even through personnel, creating a shock hazard. The size of the bonding conductor is critical. Using a conductor smaller than the 2 AWG minimum specified by the National Electrical Code can result in a high impedance path, which can limit the flow of fault current and delay the tripping of the overcurrent protective device. This delay can increase the severity of the fault and the potential for damage or injury. The bonding conductor should also be as short and straight as possible to minimize impedance. The connection between the X0 terminal and the transformer frame should be made with a listed connector suitable for the conductor size and material. The connector should be properly tightened to ensure a good electrical connection. The transformer frame itself should be bonded to the building's grounding electrode system with a grounding electrode conductor size according to National Electrical Code Section 250.66. This conductor should be connected to a grounding electrode, such as a ground rod, ground drain, or the building's metal water pipe. The grounding electrode system provides a reference point for the electrical system and helps to stabilize the voltage to ground. Bonding the panel board neutral to the panel board frame is another essential safety measure. This bonding creates a low impedance path for fault currents in the panel board and helps to ensure that the overcurrent protective device is tripped quickly in the event of a fault. The bonding should be done with a bonding screw or bonding jumper, which is typically provided with the panel board. The bonding screw or jumper should be securely tightened to the panel board frame and to the neutral busbar. The neutral busbar should be insulated from the panel board frame except at the bonding point. This insulation helps to prevent stray currents from flowing through the panel board frame, which can cause noise and interference in sensitive electronic equipment. The panel board frame should be bonded to the equipment grounding conductor, which runs back to the transformer grounding electrode system. This conductor provides a path for fault currents from the panel board to the transformer grounding electrode system. The equipment grounding conductor should be sized according to National Electrical Code Section 250.122. Mounting the insulated ground bar on the bottom or back of the panel board is generally acceptable as long as it meets certain requirements. The insulated ground bar provides a convenient point for terminating the insulated equipment grounding conductors from branch circuits that serve sensitive electronic equipment. These conductors are typically green in color and are insulated from the metal conduit or cable armor. The insulated ground bar should be mounted in a location that is easily accessible and provides adequate space for terminating the conductors. The conductors should be neatly arranged and properly supported. The insulated ground bar should be bonded to the panel board frame with a bonding jumper sized according to National Electrical Code Section 250.122. This bonding helps to ensure that the insulated ground bar is at the same potential as the panel board frame. The isolated ground conductor should be run in a separate conduit or cable from the ungrounded conductors and the neutral conductor. This separation helps to reduce noise and interference in the sensitive electronic equipment. The conduit or cable should be properly grounded to the panel board frame. It is also important to ensure that the isolated ground conductors are not inadvertently grounded to the building steel or other metal objects. This can create a ground loop, which can cause noise and interference. Let's recap the key points. Firstly, connect the X0 terminal to the transformer frame using a bonding conductor that is at least 2 AWG in size. Secondly, bond the panel board neutral to the panel board frame using a bonding screw or jumper. Thirdly, mount the insulated ground bar in a location that is easily accessible and provides adequate space for terminating the conductors. Finally, ensure that all grounding and bonding connections are properly made and tightened. By following these guidelines, you can help to ensure the safety and reliability of the electrical system. Now, let's address some common questions and concerns regarding these grounding and bonding practices. One common question is whether it is necessary to run a separate equipment grounding conductor from the panel board back to the transformer when the conduit is properly grounded. The National Electrical Code generally permits the use of metal conduit as an equipment grounding conductor as long as it is properly installed and maintained. However, there are some situations where a separate equipment grounding conductor is required, such as when serving sensitive electronic equipment or when the conduit is not continuous. Another common question is how to size the equipment grounding conductor for a branch circuit. The National Electrical Code provides tables that specify the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device. It is important to use the correct table and to select the appropriate conductor size. Another important consideration is the use of ground fault circuit interrupters, or GFCIs. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. GFCIs protect people from electric shock by monitoring the current flowing in the circuit and tripping the circuit if there is a ground fault. GFCIs should be installed in accordance with the National Electrical Code. In addition to the requirements of the National Electrical Code, there may also be local codes and regulations that must be followed. It is important to check with the local electrical inspector to ensure that the electrical system complies with all applicable requirements. Grounding and bonding are critical aspects of electrical safety. By following the guidelines and requirements of the National Electrical Code and other applicable codes and regulations, you can help to ensure the safety and reliability of the electrical system. Remember to always consult with a qualified electrician if you have any questions or concerns about grounding and bonding. The principles discussed here are fundamental to electrical safety and system performance. A thorough understanding of these concepts is essential for anyone working with electrical systems. Always prioritize safety and follow best practices when performing electrical work. Continuous learning and staying updated with the latest code requirements are crucial for maintaining competence in the field. The goal is to create a safe and reliable electrical environment for all users. By adhering to these principles and seeking professional guidance when needed, it is possible to achieve this goal. Understanding the importance of each connection and component in the grounding system is also necessary. Each element plays a critical role in ensuring that fault currents are safely conducted back to the source, minimizing the risk of electrical shock and equipment damage. Regular inspections and maintenance of the grounding system are also important to identify and correct any potential problems. This includes checking the tightness of connections, the condition of conductors, and the integrity of grounding electrodes. A well-maintained grounding system is essential for the long-term safety and reliability of the electrical system. Moreover, it's crucial to recognize that the specific requirements for grounding and bonding can vary depending on the type of electrical system and the application. For example, the grounding requirements for a separately derived system, such as a generator or transformer, are different from the grounding requirements for a service entrance. It's also important to consider the presence of sensitive electronic equipment, which may require special grounding techniques to minimize noise and interference. In addition to the technical aspects of grounding and bonding, it's also important to consider the human factors. Electrical safety training should be provided to all personnel who work with or around electrical equipment. This training should cover the hazards of electricity, the proper use of personal protective equipment, and the procedures for working safely on electrical systems. Creating a culture of safety is essential for preventing electrical accidents. Also, it's important to remember that electrical work should only be performed by qualified and licensed electricians. Attempting to perform electrical work without the proper training and experience can be dangerous and can violate electrical codes. Always hire a qualified electrician for any electrical work that you are not comfortable performing yourself. The information provided here is intended for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer for any specific electrical applications. The responsibility for ensuring the safety and compliance of an electrical system rests with the designer, installer, and owner of the system. It is their responsibility to ensure that the system is designed, installed, and maintained in accordance with all applicable codes and standards. Electrical safety is a shared responsibility. By working together, we can create a safer electrical environment for everyone. It is crucial to continuously review and update knowledge on electrical safety practices and code requirements. Electrical technology and regulations are constantly evolving, and staying informed is essential for maintaining competence and ensuring safety. Subscribe to industry publications, attend training courses, and participate in professional organizations to stay up to date on the latest developments. Knowledge is power when it comes to electrical safety. It is essential to emphasize the importance of using the right tools and equipment for electrical work. Using the wrong tools can be dangerous and can damage electrical equipment. Always use tools that are specifically designed for electrical work and that are in good condition. It is also important to use personal protective equipment such as gloves, safety glasses, and insulated tools when working on electrical systems. Personal protective equipment can help to protect you from electric shock, burns, and other injuries. In addition to using the right tools and equipment, it is also important to follow proper procedures for working on electrical systems. Always energize the circuit before working on it and use a voltage tester to verify that the circuit is energized. Lockout and tagout procedures should be followed to prevent the circuit from being accidentally re-energized while you are working on it. Never work on electrical systems alone. Always have someone nearby who can assist you in case of an emergency. Communication is key to electrical safety. Make sure that you clearly communicate your intentions to anyone who is working with you or around you. Also, be aware of your surroundings and watch out for potential hazards. Electrical safety is not just about following rules and procedures. It is also about developing a safety mindset. This means being constantly aware of the potential hazards of electricity and taking steps to mitigate those hazards. It also means being willing to speak up if you see something that is unsafe. A strong safety culture is essential for preventing electrical accidents. The ultimate goal is to create an environment where everyone is committed to working safely and where electrical accidents are rare. Every individual has a role to play in promoting electrical safety. By following the guidelines and recommendations outlined above, and by cultivating a safety mindset, it is possible to make a significant difference in reducing the risk of electrical accidents. This ultimately leads to a safer and more reliable electrical infrastructure for all. Furthermore, it's essential to understand the specific types of equipment grounding conductors EGC and their applications. The National Electrical Code recognizes several types of EGC, including wire-type EGC, metal raceways, and equipment framed. Each type of EGC has its own specific requirements for installation and sizing. Wire-type EGC are typically copper or aluminum conductors that are run alongside the circuit conductors. Metal raceways, such as conduit and cable trays, can also be used as EGC provided that they are properly installed and maintained. Equipment frames can be used as EGC for permanently connected equipment, provided that the frame is electrically continuous and is connected to the grounding electrode system. The choice of EGC depends on the specific application and the requirements of the National Electrical Code. It's also important to understand the concept of impedance in grounding systems. Impedance is the opposition to the flow of alternating current. A low impedance grounding system is essential for ensuring that fault currents can quickly and safely return to the source. High impedance grounding systems can limit the flow of fault current and can increase the risk of electrical shock and equipment damage. Several factors can affect the impedance of a grounding system, including the size and material of the grounding conductors, the length of the grounding conductors, and the number of connections in the grounding system. It's important to design and install the grounding system to minimize impedance. Moreover, it's crucial to understand the difference between grounding and bonding. Grounding is the connection of an electrical system to the earth. Bonding is the connection of different metal parts of an electrical system together. Grounding is intended to provide a reference point for the electrical system and to stabilize the voltage to ground. Bonding is intended to create a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety. In conclusion, mastering the concepts and practices of grounding and bonding is a continuous journey that requires ongoing learning, attention to detail, and a commitment to safety. By staying informed, following best practices, and seeking professional guidance when needed, it is possible to create a safe and reliable electrical environment for all.